So in this video, we're going to actually talk about how to get the molecular structure or the electron geometry, as well as the molecular geometry. And we're going to talk about some bond angles as well. So on an exam, whether you're in general chemistry 1 or 2, you may be asked to you may be given a molecular formula and say, okay, and the professor might say, well, what is the lowest structure? What is the electron geometry? What is the molecular geometry? What are the bond angles that we should expect? And so we should be able to know these. We should be able to do these things. So let's start off with a problem that's really simple, and then we're going to go to more complex problems. So let's say you're given CO2. How would you actually come up with the molecular geometry? The electron geometry, the molecular geometry, and the bond angles. Well, before I delve deep down into your business, there's a link in the description that takes you to a table that no matter what you do, you just have to memorize that table. There's no ifs or but around it. Now, maybe if your professor is nice, they may provide a table with you, table to you, but usually it's not given. So so the first thing we want to do is actually draw our lower structure. So my pattern does not change. I'm going to write out the amount of atoms I have, and I'm going to count out my total number of valence electrons. So in this case, at this point, we should know how to get our valence electrons from a table. So in this case, carbon gives me 4 valence electrons. So that's carbon, right? And we get that straight from the periodic table. And oxygen gives me 6. Again, we get that straight from the periodic table. Now, the total number of electrons that I have to place will simply be the addition of these. Now remember, because I have 2 oxygens, this becomes 2 times 6, so that's 12. 2 times 6 is 12 plus 4. So that will give me 16. That will give me 16 total electrons that I have to place. Right? So let's draw our structure. Now remember, we say that usually the atom that's furthest to the left in the formula will be your central atom. Now, starting from the basic, I could just form a single bond between both my atoms because I know that's the lowest point I can start. Now, we need to find some way to put this this structure together where we use 16 electrons and both oxygen and carbon fits the valence electrons, right? So we're utilizing all those 16. Now at this point, I've used 2 4, so we only have 4 carbons around 4 electrons around carbon rather. So, and we know carbon has to be one of those atoms that satisfy the octet rule. So I'm going to try putting a double bond between both my between both my oxygen, and now I could see that carbon actually has a full valence, right? So this becomes 2 4 6 8. So carbon is satisfied. Now what about oxygen? Oxygen is not, right? We only have 2 4. We only have 4 electrons around the oxygen respectively. So at this point, remember, carbon valence is full, so we can't really put anything else around it, but we have these lone pairs that could be your best friends, right? And what we do to the other oxygen, we could pretty much do the same because they're in the same kind of field. So this becomes 2 4 6 8. So this is satisfied, and this becomes 2 4 6 8. So this is satisfied. Now let's count the total number of electrons we've counted. So we've counted 16, and we have to make sure we have 16 here. So this becomes 2 4 6 8 10 12 14 16. So we know this is a plausible Lewis structure for the CO2 molecule. Now, what about the electron geometry? What would be the electron geometry? Now, before we start, what you guys should know, I want you guys to know, you guys probably won't see free radicals at this point in your chemistry career, but a free radical, a lone pair, a single bond, a double bond, and a triple bond all counts, right? So this is a single bond, double bond, triple bond. These all count as one electron group. This is very important, right? If you can't see this, then you will screw up the problem. So all of these, doesn't matter if it's a single bond, a triple bond, a double bond, or a lone pair or just a free radical, it still counts as one electron group. So how many electron groups do we have around the central atom, right? In this case, we only have one, which is right here, and then another one. Remember, one double bond, like we said, counts as one electron group. So this becomes 1, 2. So we only have two electron groups, right? Because we're counting groups now, it's different. 2 electron groups. So because we have 2 electron groups, the electron geometry here would actually be linear, right? And we get that straight from the table. Now, what's the molecular geometry of CO2? What would be the molecular geometry? Well, because we have 2 electron groups and no lone pairs, the molecular geometry is in fact the same as the electron geometry. So I want you guys to get this in your head. Most of the times when your molecular geometry is different than the electron geometry, it's when there's lone pairs present around the central atom. In this case, there's no lone pairs present around the central atom. Again, you could check the table again. You have 2 electron groups, 2 bonding groups, no lone pairs. The molecular geometry should also be linear. So CO2, in fact, is linear. All right. Now we start off easy. Let's go to a little bit more complex, and then we're going to wrap it up. Let's look at ammonia. So let's talk about ammonia. Now you're given ammonia on the exam and they ask you, okay, what's the electron geometry, the molecular geometry, and the approximate bond angles? And I forgot about the bond angles in the first problem, but let me revisit that real quick because that's not good, right? But CO2, essentially we had CO2 like this, right? And the bond angles, and we said that both the electron geometry and molecular geometry were linear, right? So that's the electron and molecular geometry that were linear, right? The bond angles for a linear molecule will always be 180, right? So you need to get this straight in your head. All right, let's go back to ammonia problem. So you're given ammonia on the exam and they ask you, okay, well, what is the Lewis structure, the electron geometry, and the molecular geometry, as well as the bond angles? Well, I'm not going to change my strategy. I'm simply going to write the number of the atoms that I have and the number of electrons, and the number of electrons as well, right? So from the periodic table, we should get this straightforward that nitrogen gives us 5 valence electrons. We have 3 hydrogens, but remember, hydrogen from the periodic table all on the left gives me 1 valence electron. So let's count out the total number of electrons we have to place. So because I have 3 hydrogens, this has to be 3 times 1. So that gives me a total of 3 electrons, valence electrons for those 3 hydrogens, with 1 electron being a piece. And then we have 5 valence electrons for nitrogen since we only have 1. So we have 8 total electrons to place. Now, remember we said that usually, again, our nitrogen, or the atom that's furthest to the left, is usually your central atom. So at this time, I could actually go ahead and place 3 hydrogens around nitrogen, right? And always start from the lowest. I'm always going to start by forming a single bond. And it's simply because it is the smallest space I could start without over exaggerating anything. I could always build up from this spot. Now, one thing that's helpful with it in this case is that remember that hydrogen only has 1 valence electrons. That means that it can only form 1 bond. So in this case, hydrogen will never satisfy the octet rule. However, we know that nitrogen has to. Now, let's count how many electrons we've placed thus far out of the total that we have to place. So this becomes 2, 4, 6. So we've placed 6, but we need 8. Now remember to say that hydrogen at this point is fully occupied. So the only other place that we could put our additional 2 electrons would actually be on the nitrogen. So this would be the Lewis structure of ammonia. Now, what would be the electron geometry? What would be the electron geometry? Well, The electron geometry is straightforward. I'm just counting the electron groups. So we have one single bond, that's one electron group, another single bond, that's one electron group, another single bond, that's one electron group, and we have a lone pair. In this case, it's still one electron group. So we have 1, 2, 3, 4. So that's 4 electron groups. And if we have 4 electron groups, that electron geometry is tetrahedral. Now, let's talk about the molecular geometry. All right, so let's talk about the molecular geometry. What would be the molecular geometry of this? Pause the video and try to answer it. Well, I have 1, 2, 3, 4. I have 4 electron groups, but now I have a lone pair. I actually have a lone pair. And so if I have 4 electron groups, with one being a lone pair, this is considered trigonal. This is considered trigonal pyramidal. So the molecular geometry is now trigonal pyramidal. So notice here now that the electron geometry and the molecular geometry are 2 different things. So in the real world, this wouldn't be something on the exam that you will give to your professor if they ask you about what the molecule actually look like or the molecular geometry. The electron geometry is just an imagination of how we could represent the 3D structure on paper, right? But it's not an accurate representation of the 3D structure. And so really what the molecule really looks like is a trigonal bipyramidal. So it looks something like this. And this would be something that will be plausible for how the molecule really looks, right? Now, with a trigonal pyramidal structure, right? So with a trigonal pyramidal structure, the bond angles typically are usually less than 109. All right, so the bond angles are usually less than 109.5, and you might be saying to yourself, okay, why is it not 109.5? And it's because of the presence of these lone pairs. So you could think about the presence of lone pairs squeezing or moving these hydrogens closer together than what they ought to be, and so that's why we say it's less than 109.5. All right, so that one's pretty straightforward. Let's go to a more complicated one. Let's say you're given ICl4 minus. How would you do it? How would you do it? Well, the first thing I'm going to do is write the number of the my atoms and the amount that I have. I want to count out the total number of electrons. So we know that from the periodic table, iodine gives us 7 valence electrons. Chlorine gives us also 7 valence electrons. So how many valence electrons do I have to place total? Well, I have 1 iodine, so that's just 7. But I have 4 chlorine, so this would be 4 times 7, right? And the 4 times 7 is 28. Plus 7 should give me 35. But remember, we have a negative charge here, and that means that we have to add 1 electron. So that becomes 36 electrons total that we have to place. Now, again, like we said before, usually, or central atom is the atom that's furthest left in our molecular formula. So at this point, we could actually just draw our I in the middle. And at this point, I'm going to place 4 chlorine around it, right? Because that's what the formula is telling us. And at this point, let's form single bonds, right? Remember, that's what we said, right? Starting from the singlest part, the most simplest form is in the form of single bonds. Now, iodine, right? In this case, is one of those weird atoms, right? The octet usually is full, but remember the octet rule kind of becomes shady when we're dealing with ions, right? So neutral compounds, we might say, okay, well, you might expect the iodine atom to just have 8 electrons, but when we deal with ions, it becomes a little bit weird, right? So at this point, let's act like our iodine valence is filled. So this becomes 2, 4, 6, 8. So iodine is satisfied for right now. What about chlorine? They're not, right? We only have 2 electrons around each of our chlorine. So at this point, we could actually form lone pairs around our chlorines. And that, in this case, will satisfy our octet, right? So for the chlorine, it will be 2, 4, 6, 8. And so this would be good. I could do the same thing here. And this will be 2, 4, 6, 8. So this chlorine is satisfied. And I'm going to do the same thing for the other as well. Right? So in this case, let's count the total number of electrons we've used thus far. So this becomes 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So that means that we've used 32 electrons, but we have 36 to place. Now remember, chlorine is already full, so the only other place I could put the other remaining 4 electrons would actually be on the iodine atom itself. Now remember, this molecule is charged, so the lowest structure we'll actually have to put in brackets and put our charge there. Now obviously I could tell you now the iodine is the atom that has the negative charge on it, but this video is not really pertaining to formal charges, right? We have another video that looks at formal charge. But so this would be just the lowest structure for the ICl4 ion. Now, what is the electron geometry? Pause the video and try to figure it out. Right, what would be the electron geometry in this one? Right, let's count the total number of electron groups we have. So this becomes 1, 2, 3, 4, 5, 6. Right, so we have 6. We have 6 electron groups, and if you have 6 electron groups, that's an octahedral. We say that's an octahedral. So please do not confuse octahedral in just your regular mind as being 8. In chemistry, when we talk about octahedral, we talk about electron groups of 6. So what would be the molecular geometry? Right? So we talk about the electron geometry being octahedral, but what would be the molecular geometry? It so happens that if you have 4 bonding groups and 2 lone pairs, the electron geometry here is actually square planar. Now, if you're saying to yourself, how am I getting these? Well, there's a table that, I'm sorry, if your professor is really kind, then you might have it on the exam, but usually it's not given so you just have to memorize with respect to the bonding groups and the lone pairs and how the structure look, right? So on paper we say the electron geometry is octahedral, but in reality it's really square planar. And so if we really want to draw an accurate representation of the molecule, what really we're dealing with here is something that looks like this. Right? Now, obviously the lone pairs are here, and I'm going to put in my electrons. Right? Really just drawing the same structure, so nothing to be confused about. But really what we're saying is that the structure actually looks like a square. And in square planar, we're really just forming 90 degrees angles. So these are actually, the bond angles here would actually be 90 degrees. Right? So another classic example of the electron geometry and the molecular geometry not being the same. Let's look at another one. Let's go to a simpler one this time, and let's ramp it up again. Methane. How are we going to do methane? Well, we first need to figure out the lowest structure. Again, I'm not going to change from my strategy. I'm going to keep on doing the same thing. I'm going to go to the periodic table, and I'm going to see that carbon gives me 4 valence electrons, and I'm going to see that hydrogen gives me 1 valence electrons. So the total number of electrons I have to place at this point would be 4 hydrogen times 1, so that'd be 4, plus 4, so that'd be 8 total electrons I have to place. All right, again, our central atom is usually an atom that's in first place, and so at this point I could actually just place 4 hydrogens around my carbon. Now, like I said before, the simplest place to start is to just form single bonds, and then you could build up from there. What you don't want to do is start forming double bonds initially, right? Or triple bonds, or right? It doesn't work like that. That's not how you, well, there's not a specific way of drawing Lewis structures, but the better way, or a better way of approaching these problems would be to start from the bottom. So let's count the total number of electrons we've used, and let's see if this matches the number, the 8 that we've counted. So this becomes 2, 4, 6, 8. Okay, so this is a plausible structure for methane. Now, what is the electron geometry? Right? If we have 4, so let's count the number of electron groups we have. It becomes 1, 2, 3, 4. So if we have 4 electron groups, no lone pair, this is actually tetrahedral. Now, what would be the molecular geometry? Well, again, we have the presence of, pause the video and do it. We have the presence of no lone pairs. So essentially, electron geometry and the molecular geometry is actually the same for methane. So pretty simple to get us kind of ready for another hard one. Now, this is not an accurate representation of the molecule, obviously. So when we talk about a tetrahedron, really what we're saying is that the molecule looks something like this. All right. So really what we're saying is that electron geometry is a poor schematic representation of what the molecule actually looks like. Right. The molecular geometry is what really tells us. What's going on. Now, the bond angles for these, for tetrahedral, is exactly about 109.5. Now, let me ask you a question. Let's say I had some lone pairs on the carbon. Not that it's possible, and you shouldn't be thinking about that, but for argument's sake, let's say I had maybe a lone pair on the carbon. Would you expect the bond angles to be greater than 109.5 or less than? Right? Tell me what you think, and the answer would be less than, right? So the idea is that lone pairs, because they're of higher energy, they cause some sort of distortion and would be able to push these hydrogen closer together. Right? So that's an experimental thought. Let's do another one. Let's do SCl6. Well, to get lower structure, I'm not going to change what I've done. I'm going to write my sulfur and I'm going to write my chlorine, but I have 6 here. Now the total, well, 6 here. Now the valence electrons that I get from sulfur is on the periodic table, and that's 6. Chlorine, that's really 7 valence electrons. Is everyone with me thus far? So well, I mean, let's do a different one. I mean, I don't want to do this one. Let's do BRF3. Oh man. How do we do BRF3? Well, we have bromine, we have 3 fluorines. Right? From the periodic table, bromine is going to give me 7 valence electron. Fluorine is also going to give me 7 valence electrons. So the total electrons I have to place would be, in this case, 3 times 7, which would be 21, plus 7. Right, so 3 times 7, which would be 21, plus 7. So I have 28 total electrons to place. So again, usually our central atom is going to be our atom that's first in the problem at this place. At this time, I could actually place 3 fluorines around my bromine, and I'm just gonna simply form single bonds at this point. Right? Always start from the bottom. Now we need to find a way to put 28 electrons and specifically fill fluorine's octet. Now this becomes, I'm gonna write my fluorine as this, right? So I have a single bond with 2, 4, 6, 8 electrons. So my fluorine is full. I could do the same thing here, and I could do the same thing on this side. So this becomes 2, 4, 6, 8. So this fluorine is good, this fluorine is good, this fluorine is good. So let's count how many total electrons we've used thus far out of the total, and let's see if they match, right? So this becomes 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Right, so that means we're deficient in 4 electrons. Now, because fluorine octet, it's full, that means that the only other place that we could put the additional 2 electrons would actually be on a bromine atom. So what would be the electron geometry here? What would be the electron geometry? Can you pause the video and figure it out? Well, in this case, we have 1, 2, 3, 4, 5. So if we have 5 electron groups, let me get this out of the way, but if we have 5 electron groups, that corresponds to a trigonal, what we call a trigonal bipyramidal. Now what would be the molecular geometry? What would actually be the molecular geometry? Well, I have 5 electron groups, but actually 2 is actually lone pair. So if 2 is lone pair, this is a weird one. We call it a T-shaped. So the molecular geometry is T-shaped. And in fact, I pretty much drew it like a T-shape, right? So again, this is an accurate representation of what the molecule of what the molecule really looks like. Now, the bond angles that you'd expect in a T-shaped molecule would actually be less than 90 degrees. And could anyone guess why? And I'm singling them out here, but it's the presence of these lone pairs. And it's a theme that we've talked about, and you got to think to yourself, you got to say to yourself, if there's lone pairs on the central atom, they're going to cause distortion, kind of pushing the atoms closer together. So it's a concept that you must try to put in your head, right? So in this case, it wouldn't be 90, but less than 90. Let's do one more. It's an easy one, but let's say on the exam you're given, let's say you're given BCl3. How would you do it? Well, I'm going to write boron, I'm going to write chlorine, but I have 3. Let's count the total number of electrons I have to place. So boron from the periodic table, it gives me 3 valence electrons. Chlorine gives me about 7 valence electrons. Now, to get the total electrons, we must multiply as our common theme throughout this video. So this becomes 3 times 7 because I have 3 chlorines. So this becomes 3 times 7, which is 21, but we have 3. So that gives me 24 electrons total. Now, as usual, we said our central atom is usually an atom that's first in the formula. So I have boron, and at this point I have 3 chlorines around it. Now, please remember, and I'm glad I did this problem, please remember in your classes, boron is one of the exception to the octet rule, right? Which means that you shouldn't be surprised if boron does not satisfy the octet rule in your Lewis structure. So at this point, I'm going to form single bonds, and at this point, I'm going to form single bond. Let's see how many electrons we've used thus far. So this becomes 2, 4, 6. So this becomes 2, 4, 6. So we've only used 6 out of the 24 that we have to place. So we need about 18 more. Now, boron at this point is satisfied, and the reason why we say it's satisfied because it only has 3. It has 3 valence electrons, so it can only form 3 bonds, right? So boron is satisfied. So it has 3 valence electrons, can only form 3 bonds. That means that the maximum amount of electrons we should see around boron in a non-charged state should be about 6 electrons total. Right now, if we're talking about ions, it kind of differs, right? So ions are kind of out of the way. We have to adjust with ions, but neutrally charged molecules, we should expect about 3 bonds for boron, or a maximum of 6 electrons around boron, because it can only give 3 bonds. Now, at this point, our chlorines are not satisfied, but we could fill in the pairs of lone pairs and see where that takes us. Now, just before we continue, in chemistry, we have to recognize patterns. And so our halogens, when we're drawing Lewis structures, to make them really easy for you, I'm going to replace my R. So let's say my R is in the halogen, and X, let's say R is the R group. So that means it could be anything. Let's say R group, it could be anything. But X is my halogen. The pattern around halogens as in bonds is that they usually carry around 3 pairs of lone pairs with a single bond, right? Usually that's how you see halogens in molecular formula. So that's those are patterns of Lewis structures that we must see, right? So at this point it becomes 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we've counted 24 electrons and we've used 24 electrons. Or chlorines octet are satisfied, and a boron, let's say pretended octet is satisfied, right? So this is a good structure for a BCl3 molecule. So what would be the electron geometry? Right? Well, when we have 3 bonds, but no lone pairs, this is actually called a trigonal planar. Right? This is actually called trigonal planar. So what would be the molecular geometry now? Well, remember the theme is kind of present here, right? If the theme is kind of present here, if there's no lone pairs around the central atom, in most cases the electron geometry and the molecular geometry you would expect to be the same. And so in this case, the molecular geometry is also trigonal planar, right? So really, when really more accurate representation of the molecule is a trigonal planar. So that means I have boron, right? And you have to kind of picture this as being flat, right? So this is more of an accurate representation of the molecule, and ignore this. This was a mistake, but this is not a lone pair, right? But this is a more accurate representation of the molecule. Now, the bond angles for in a trigonal planar, ideal trigonal planar, these are usually 120. Now, I'm going to ask a question again. What if I had lone pairs on the boron? Would you expect the bond angle to be less than 120 or be greater than 120? Actually, I want you guys to answer that in the comments. Now, so this would be the end of the video, and I hope it helps. Again, if you have any questions, I'm always responding in the comments, so be sure to ask questions.